thank you for coming to this rendition of the KITP Innovate seminar with NSBP. Today we are happy to have Alexandria Udenkwo giving us a talk today. So Alexandria Udenkwo is a fourth-year physics graduate student at Washington University in St. Louis. She's an experimental quantum physicist in the Merch Lab. Her interests involve quantum thermodynamics and measurement theory, and she is an alum of UMBC and the Meyerhoff program. So today she will be giving us a talk called How to Quantize a Circuit. So take it away, Alexandria.
Thank you so much for the introduction, and thank you for everyone who has been able to come to my talk. I'm really excited to talk about the very exciting field of circuit quantum electrodynamics and how we use this field to be able to make macroscopic circuits in order for us to study quantum effects. So the outline of my talk will go as follows. So first, I'll talk to you guys about macroscopic quantum effects, which include superconductivity and Josephson junctions. And then we'll talk about what exactly we do with Josephson junctions in the adjacent field of cavity quantum electrodynamics and how this relates to spontaneous emission. And then we'll create the quantum circuit. And then we'll talk about controlling and measuring our quantum circuit, and we'll talk about applications, in particular, a project I've been working on that studies engine cycles in regards to qubits. So first of all, why circuit quantum electrodynamics? So the novelty of circuit quantum electrodynamics is the ability to be able to fabricate a circuit, which is made of billions upon billions of atoms. We're able to take this circuit, and it allows us to simulate the dynamics of a single two-level atom interacting with a resonant cavity. But how do we get here, and why is this possible? Well, when we talk about quantum mechanics and we think about quantum systems, we think about microscopic quantum systems, right? So we're sort of used to studying like the wave functions of either one particle or two particles by applying the Schrödinger equation. And famous examples include the hydrogen function for the hydrogen atom, as well as the quantum harmonic oscillator for a particle trapped in a harmonic oscillating potential. But what happens when we study systems with many particles, on the order of 10 to the 22 particles, like lots and lots of particles, right? Well, usually at larger scales, we're able to sort of understand and apply to these systems the laws of Newtonian mechanics, right, in order to understand these systems. However, there are microscopic systems in nature where collectively their billions upon billions of degrees of freedom behave according to quantum mechanics. Examples include superconductivity, superfluidity, Bose-Einstein condensation, the Josephson effect, the quantum Hall effect, giant magnetoresistance, and topological order. Very famous examples. But today in my talk, I'll be talking to you guys about about specifically superconductivity and the Josephson effect, and how these directly allow us to be able to make our quantum circuit. So first, let's talk about superconductivity. So studying the energy of a system at low temperatures, we're able to reduce the number of states that this system can occupy. So think of a metal, for example, and suppose that it is superconducting. The following is going to happen. Well, as we cool the metal down to its critical temperature, the electrons in the metal are going to form bond states called Cooper pairs. Since the electrons are pairs, they act like bosons. And we know from our quantum mechanics books that bosons can collectively be all in the same state, right? And since our metal is below the critical temperature that would make it superconducting, these bosons collect in the ground state, for instance. And since all the electron pairs occupy the same state, there's no resistance and current can flow, right? Because usually when it comes to current, the electrons are in different states, and so they're sort of lowering the current. But since they're now all in the same state, current is able to flow with no resistance, and that's how we come up with superconductivity. An example of superconductivity is the Meissner effect, right? So suppose we have a metal that can become a superconductor, okay? We put this metal in a magnetic field, and then we cool it down to its critical temperature. What ends up happening is that the magnetic field changes the flux within the metal, which then induces an opposing field by Lenz's law, because a supercurrent is generated, right? And since a supercurrent is generated, the magnetic field that the supercurrent generates expels the magnetic field. And so what we see in this GIF here is we have the superconductor. You see it's like really cold because like we have to get it down to its critical temperature. And then we see a metal. Oh, sorry. We see a magnet that is levitating over the superconductor, right? And this is the Meissner effect. So we see that in the superconductor, it has a supercurrent that is repelling the magnetic field of this magnet. So what superconductivity actually leads us into the Josephson effect. So what would happen if I had two superconductors and I put a barrier in between them? So suppose we have two identical superconductors separated by a thin insulating barrier. Superconductor 1 corresponds to the collective state psi 1, and superconductor's 2 state is psi 2. And suppose we set a potential difference between the two superconductors. Then the Schrodinger equation gives us these two equations, respectively. If we were to define psi 1 and psi 2 as the following equations, we have that theta 1 and theta 2 are the phases of the superconductors, and rho 1 and rho 2 are the charge densities of the electrons. So like how many electrons are in our the charge density of the electrons in the superconductors, respectively. Then we're able to take these equations, substitute them in, where we define a parameter delta, which is the difference between the two phases. Simplifying these equations, we get these two equations where J is the current density. So going back to how I was explaining how in superconductors we generate these supercurrents. So J here would be the current density. Delta is the phase difference between superconductor 1 and superconductor 2. And then we have Q corresponding to 2E, where we know that because we're tunneling Cooper pairs, a Cooper pair is going to have a charge equal to 2 times a regular electronic charge, right? Okay, I'm going to end up replacing J here with I. I'm going to redefine the current density J to a current I and replace this this delta with psi, and we get the Josephson junction. We get the Josephson equations, and so these are the infamous Josephson equations, where IC is the critical current of the junction. Okay. So these are the famous Josephson equations that tell us how a Josephson junction is supposed to act and sort of how the quantum tunneling is facilitated. For example, let's look at the second equation. Suppose that V of t is a DC voltage, so my voltage that's biasing these two superconductors. If V is 0, we see here that psi of delta phi delta t is equal to 0, and so then sign is a constant, right? So this is implying actually that if our bias, if our voltage bias is 0, we actually are able to get a current that has a value between our critical current negative IC and positive IC. And this is really, really cool. The fact that we're able to induce a current within our Josephson, our two superconductors and insulating barrier. This is really, really cool that we're able to induce this current without needing a voltage bias, right? And so, utilizing the Josephson effect, we are able to make a Josephson junction, which produces current that doesn't require a voltage source. A common way to fabricate Josephson junctions requires using two pieces of aluminum, with aluminum oxide being the insulating barrier. So as you guys can see in this diagram here, we see here that on the bottom and top we have aluminum and aluminum, which is superconducting, and then we have the aluminum oxide, which is our barrier. And we're able to facilitate quantum tunneling, which is described specifically by those Josephson equations, right? So then using the Josephson junction, we're able to sort of do a lot of really interesting stuff. So keep that in the back of your head. Now we sort of go into cavity quantum electrodynamics. Cavity quantum electrodynamics is the study of the interaction between light or radiation and matter. Einstein showed us that in order for a light-matter system to reach thermal equilibrium, spontaneous emission must happen. However, for this to work, the interaction between the matter and the vacuum modes surrounding it must be studied, right? So we have matter, we have light, and then we have the vacuum modes surrounding that light-matter system. And so what is going on in the system? How do these two things interact? So what exactly is spontaneous emission? So suppose we have a one electron atom that can be described by a two-level system. Spontaneous emission occurs when the electron jumps from the higher energy state to the lower energy state, where here we're emitting a photon. This can be understood as the coupling of the electronic state to one of the many vacuum modes surrounding this two-level system, right? So we have our two-level system surrounded by the vacuum by an infinite number of vacuum modes, right? We can actually manipulate the rate at which spontaneous emission occurs by manipulating the density of vacuum modes the electron could possibly couple to. And this specific rate is characterized by Fermi's golden rule, right? And I'll remind you guys about Fermi's golden rule. So suppose the rate at which the probability of a photon being emitted per unit time is given by gamma naught. If the coupling between the atom to each vacuum mode is given by omega Eg, where Eg just denotes like the lower and higher energy states, is given by this equation here, where dg is the electric dipole moment between my two energy levels, and then E is just the electric field of the surrounding vacuum. Then the density of vacuum states is then given by this density of states equation, where V corresponds to the volume per qubit meter, the volume of the vacuum modes. So then Golden's Fermi rule then tells us that our spontaneous emission rate is given by this coupling between the vacuum mode and our atom, as well as the density of states. So these two multiply together, right? So these two are really, really important. The fact that we're able to sort of manipulate the density of states in order to tune like how much our system, our atom light system, can spontaneously emit. So we introduced the cavity in order to do this manipulation of the vacuum modes. You can think of a cavity as two mirrors. If we trap a photon in between these mirrors, it'll bounce between them, right? The goal of the cavity is to manipulate the rate of the spontaneous emission gamma naught, so that the two-level system has as much or as little spontaneous emission of the photons as possible. For the purposes of circuit quantum electrodynamics, we want as much spontaneous emission as possible between the two-level system and its cavity. This is so that we can explore dynamics described by the Jaynes-Cummings Hamiltonian, as shown here. We'll come back to this Hamiltonian later, but this Hamiltonian essentially describes what it would mean for we have our cavity and then we have our two-level atom, and what would be the dynamics and the energy of this system. And so for now, let's just explore what is required of a cavity in order to get a high spontaneous emission rate. Let's take our so for circuit quantum electrodynamics, we want to increase, we want our spontaneous emission rate to be high. So in order to do that, let's take our two mirrors and sort of curve them. This is so that we can keep the photons in the cavity as long as possible. This kind of cavity is referred to as a Fabry-Perot cavity. A resonant cavity such as this enhances vacuum fluctuations, defined by the ratio, again bringing back this omega Eg, which corresponds to the rate at which fluctuations happen between the atom in our and the vacuum, and the cavity line width corresponding to, or the cavity bandwidth corresponding to delta omega c. This and we require this ratio to be larger than 1. The reciprocal of delta omega c, which is the quality factor, this describes the density of modes that the atom can see in the cavity, right? We want this quality factor to be as high as possible, such that the spontaneous emission becomes reversible and the atom and field resonantly exchange the excitation at rate omega Eg. So we want the sort of photon to be bouncing around this cavity, if you can sort of think about it like a ping ball machine. So we sort of want this photon to be bouncing around the cavity, interacting with our atom as much as possible, so that we can get the spontaneous emission, high spontaneous emission rate for a resonant cavity. And from this, actually, from being able to increase our spontaneous emission rate, the exchange dynamics are described by the Jaynes-Cummings Hamiltonian. And it tells us that the interactions between our two-level system and a resonant cavity give us vacuum-Rabi oscillations. So you can sort of think again as our photons are interacting with our atom, we can sort of think about how our atom is then spontaneously emitting this photon. And we can sort of plot the population of our atom as a function of time. So as you see here at first, we see that the probability of our atom being in the ground state in this case is 1. So like the atom is in the ground state. And then this photon is then interacting, this photon is again interacting with our atom, and so they're exchanging resonantly due to the fact that we have made a resonant cavity such that the atom is always exchanging between the cavity and the atom, such that we go from the ground state to the excited state to the ground state to the excited state, and we get these nice vacuum-Rabi oscillations between the vacuum and our atom. Here specifically in this diagram shows specifically how much time it would take for the atom to go from the ground state to the excited state, and we refer to this as sort of the pi time. So as the pi time. In circuit QED, we can make the equivalent of a Fabry-Perot cavity using circuits. The best candidate for the job is the LC circuit. However, with circuit QED, the operating frequencies are in the microwave range, which actually requires us to make our resonator a transmission line. And a transmission line actually can be modeled by a series of LC circuits. So here below we have a coplanar waveguide resonator, which is sort of a transmission line here. You can sort of think of transmission lines as like coax, you can sort of think of transmission lines as like our way of sending our photons to whatever system that we're studying. And so here we have our transmission line, and then here you see these tiny little LC circuits. As you can see here, the capacitor and the inductor here, and you see like we can sort of model this transmission line by all of these LC circuits. And then here would be specifically our two-level system. And I'll get back to this later. So now that we have all the ingredients that we need, we know about the Josephson junction, we know about how spontaneous emission allows us to actually interact with our two-level system. Now we can make a quantum circuit. So first, the two-level system. A good starting candidate to use to model our two-level system is the LC circuit. Its Hamiltonian is given here by h is equal to q squared over 2c plus phi squared over 2l, where q is the charge, c is the capacitance, l is the inductance, and phi is the flux, right? This Hamiltonian is classical, but we want to understand a quantum mechanical system, right? So in order to describe the system quantum mechanically, we need to make the charge q and flux by variables quantum operators, right? And so they must satisfy the following commutation relation here, where we have this commutation relationship between the flux and the charge as always equal to I h bar. Another thing that we need to consider is that in order to make a two-level system, we need to be able to probe individual energy levels. If you guys think about the LC circuit, it corresponds to a quantum harmonic oscillator. And as we know with quantum harmonic oscillators, each energy level is evenly spaced, right? So let's say I were to try to control my two-level system with some probe tone. If I were to send down a probe and try to control the levels, I wouldn't be able to because the probe tone would excite each level. So I wouldn't be able to specifically choose, let's say, this like 1-2 transition here. I wouldn't be able to choose that, right? So what's lovely about the Josephson junction, so instead of having my regular inductor, I replace it with my Josephson junction. What's lovely about the Josephson junction is that it introduces a nonlinearity such that it makes the spacing between each energy level different, so that if I were to send a specific frequency value, I can probe correspondingly that energy level, right? So here for the 0-1 transition, I specifically send in a frequency that corresponds to that specific transition. So I'm able to have like specific control over my energy levels. So continuing with our two-level system, using the commutation relations, we get the quantum Hamiltonian, we get the quantum mechanical Hamiltonian for the LC circuit, as shown here, where EC is E squared over 2C, which is the capacitance, phi is the reduced flux, and EL is the inductor energy. Sorry, I meant the capacitance energy here. And then replacing that inductor with our Josephson junction, our Hamiltonian becomes the following here, where EC is now, we've added our Josephson junction, which actually adds in capacitance. So EC now changes to CJ, corresponding to the capacitance due to the Josephson junction, plus CS, corresponding to the capacitance due to the shunt, as shown here. And then this energy, this capacitance energy, this is the charging energy required to add Cooper pairs to our superconducting islands. So if you guys remember, you have two superconductors and then you have that insulating barrier. And this gives us the amount of energy that would allow us to be able to add Cooper pairs. And then EJ is the Josephson energy of our Josephson junction. And then N is our reduced charge, corresponding to the charge divided by 2E, because again, with Cooper pairs, we have 2 electrons. Okay, so we have our two-level system corresponding to a Josephson junction plus the capacitor that shunts this Josephson junction. So this is our two-level system here. and then combining it with our coplanar waveguide resonator, which again, as I mentioned before, you can sort of think of as a series of LC resonators, we are then able to use spontaneous emission to be able to facilitate interaction between our two-level system and our sort of cavity here. So our resonator, right? And so this allows us to facilitate interactions between our qubit and our microwave photons. And so here we have our circuit QED system. So here now we have our quantized circuit, right? A way to represent this circuit element here, where the Josephson junction is shunted by this capacitor, we call this the transmon, and we denote it by a plus sign here. So now we want to be able to control and measure our quantum circuit, right? So in lab, we work on a 3-qubit chip. So here is the full qubit chip, and here are the controls, right? So first we start with the drive lines. So we have these 2 qubits here that are controlled via drive lines. What drive lines do is that each qubit has a resonant frequency, and we send through the drive lines the resonant frequency of the respective qubit in order to drive the qubit into resonance, right? In order to drive the qubit into resonance. So that's what these 2 drive lines do here. So so that we can control our qubit. And then these 2 fast flux lines, what they do essentially is that these 2 qubits are flux tunable, right? So what does flux tunable mean? Flux tunable means that we're able to resonantly, change the resonance frequency of the qubits. We're able to change the resonance frequency of the qubits such that the resonant frequency changes due to the flux that I send through these flux lines. So I can like change the resonant frequency. And then here we have the readout resonator. So here again we have the qubit and we have the readout resonator system, right? So how exactly am I going to get information about what is the state of my qubit? I do that through I can also do that through my resonator, right? So here I here I come back to the Jaynes-Cummings Hamiltonian. In the dispersive limit, and what I mean by dispersive limit is it's a limit that allows us to determine, it's a limit that allows us to facilitate us being able to control or get information about our qubit through our readout resonator here. And this, in order to do that, we know that if we see a shift of our resonator's frequency by a value of chi, we're able to actually read information about what state our qubit is in, whether it's in the ground or the excited state. So these readout resonators facilitate us being able to get information about the qubit without directly measuring the information about the qubit and ruining its qubit state, its quantum state. So now we can get into applications. So I'm going to talk about a project that I've been working on. It's essentially, as named here, entanglement and local measurement field CQED engine. So essentially, as was mentioned in the intro, one of my interests is in quantum thermodynamics. And quantum thermodynamics gives us insight into the dynamics of open quantum systems. So if we have a Hamiltonian, we can sort of denote this Hamiltonian as sort of like the work in thermodynamics. If we have a Lindblad, we can sort of think of this as like the heat dissipated from our system. And if we have a decoherence rho, we can sort of think of this as like the entropy, right? So we can sort of map quantum mechanical properties onto properties that come from thermodynamics, and we can also study these properties of thermodynamics using our quantum system, using the system that we just built for the last couple of minutes. So in order to sort of study the thermodynamic properties, we can sort of study these properties in a sort of measurement fueled engine. So we can sort of create an engine cycle that can study how local measurement breaks entanglement. So like say I have two qubits that are entangled and I do a measurement on one of them. I end up breaking the entanglement between I end up breaking the entanglement between the two qubits, and I can use the engine cycle in order to study this phenomena. We can also study the binding energy of entanglement that can then be harnessed as fuel. So we can sort of use the entanglement energy of our two qubit system and use this as fuel for our entanglement engine. And so these processes actually occur because our system Hamiltonian, so our Hamiltonian describing our system, and our measurement Hamiltonian, the Hamiltonian that we use to measure our system, they end up not commuting. And when these two Hamiltonians end up not commuting, it can lead to back action, it can lead to strange things in like the energetics of our quantum system, but it can also lead into insights into the limits of how I'm able to measure my system in general. And so here the experiment, in order to do this experiment, in order to create this engine cycle, we use our three qubits here where I denote each of these as QA, QB, and QC, where each of them have specific frequencies, omega A, omega B, and omega C, right? So first, I set up the initial state, where the initial state here is 1, 0. So I set qubit A in the excited state. I set qubit A in the excited state. And then I want to entangle qubit A and qubit B. How will I be able to do that? Well, in our system, we're able to actually use omega C in order to induce coupling between omega A and omega B. And this is described by this Hamiltonian here, where this Hamiltonian is the local Hamiltonian corresponding to the two qubits. And here is the non-local Hamiltonian corresponding to the entanglement between the two qubits. Then, now I have my entangled state, as described here by this equation here, where 1, 0 corresponds to the excitation being in qubit A, 0, 1 corresponds to the excitation being in qubit B. And this is the state that my system evolves into. So then, as my system is entangled, I want to extract energy using local measurement, right? So how will I be able to do that? Well, I do this at a specific time. At a time where omega corresponding to the Rabi frequency, or the frequency at which this excitation hops between qubit A and qubit B, the excitation has a max probability of being on QB, so being in the higher energy level state. Local measurement, we know that local measurement ends up breaking the entangled state between qubit A and qubit B. And so if I am able to measure this excitation at t equals pi over omega, then I'm able to get extra energy from my system. Because remember, we started here at this energy level, omega A. And then I measure here. So I actually get a gain in energy from my system. So ideally, we're able to facilitate this engine cycle with perfect projective measurements. And we're able to measure the local state of our qubits, right? And so being able to do these measurements, we're able to see these nice vacuum Rabi oscillations between the two qubits. And we can do this for various values of coupling strength, where omega corresponds again here to g squared, where g is the coupling strength between the two qubits, and delta, which is the detuning between omega A and omega B. Okay, so here is a diagram showing what I described before. So we have this nice oscillation. And so then I do my measurement at pi over omega, and I'm able to get a gain in energy from where I started. And then for various values of the ratio g over delta, I'm able to measure how much energy I'm able to get, as well as the entropy that is produced from the system as well as the efficiency of my system. And we see ultimately this energy comes from the fact that I'm doing this measurement on my entangled system. So now the next sort of question for the system is that, are we able to implement local measurements in circuit quantum electrodynamics? So going back to our readout resonator here. So we have a reader resonator. Photons are able to populate the readout resonator at the induced measurement rate gamma, where gamma here corresponds to, as I mentioned before, that dispersive shift, the number of photons in the resonator, as well as kappa, where kappa you can sort of think of like if you have your two mirrors, like how transparent the mirrors are. So like how much depending on the transparency of the mirrors, like either the photon's going to leak out or not. So you can sort of think about it as the rate at which photons leak out of our resonator. And then we have our induced measurement rate, where like this gamma is then multiplied by the efficiency at which we're able to obtain information about our quantum state. Measurement actually ends up competing with the coupling rate omega. Ideally, we want to be able to get as much information as possible, even if measurement is competing with this coupling rate. However, this can be really challenging in quantum circuit QED, as the measurements that we do using the readout resonator can be pretty slower compared to the coupling rate. However, if we sort of straddle the intermediate measurement regime, where the induced measurement rate is on par with the coupling rate, we can actually study pretty interesting dynamics. So here we actually have here the two paradigms I described before. So here, this specifically represents the ideal regime, where coupling is sort of turned off before measurement, right? So we have the ideal regime where it's like coupling can immediately turn off, measurement can immediately turn off coupling, right? So we see these nice vacuum Rabi oscillations. But here we have our experiment where we have the measurement turn off coupling. We leave coupling on as we're doing measurement, right? And so here, as you can sort of see in this diagram, here in this regime, where we don't really see any oscillations at all, we see that the coupling rate is sort of winning over the amount of the rate at which we're able to obtain information about our system. But here we're sort of straddling this intermediate regime where we're able to see oscillations between the two qubits, right? So here we're sort of in this intermediate regime, right? And so what's great about this system is that we're able to actually understand fundamental limits of the measurement accuracy of our system with global conservation laws are present. So remember, the reason sort of why these two items of coupling and measurement are competing is because their Hamiltonians don't commute. And this is because there's a conservation law that is causing these Hamiltonians not to commute, right? And so these conservation laws require that the total energy between the qubit and the meter is conserved, right? And so this limits our ability to measure. This limits our ability to immediately measure how much to measure precisely information about our qubit. So we can actually quantify this using the Wigner-Araki-Yanez theorem, as well as Oslo's bound, and this quantifies the inaccuracy of the measurement of our system in general. And so we've been doing a lot of work with this project, and I'm hopefully wrapping up, and I'm really excited for that. So thank you so much, everyone, for attending my talk. Do you have any questions?
Thank you so much, Alexandria, for that talk. That was very enjoyable. So Carlton will be handling questions, so please put them in the chat for Alexandria. And I think I'll start us off until we get some more questions in. But I had a question. So the Jaynes-Cummings process that you mentioned for the resonator in the cavity, it looks like remarkably similar to how a laser first starts off with a spontaneous emission and between cavity walls. And I guess the main difference there, I guess, is that we're working in vacuum and not with a gain medium. Is that correct? Is that the main difference between this and a laser to start off with, at least?
So I mean, the lovely thing about circuit QED is that it directly takes from the work that a lot of like optical systems use and stuff like that. So like, yes, like as what you're saying with like when it comes to like lasers and stuff like that, the Jaynes-Cummings Hamiltonian also directly applies. What did you mean exactly by like gain medium? Because I would say you can actually apply this Hamiltonian, well, maybe you do a little manipulations to a laser system, I think. But I don't know. I'm not really sure. But I don't know. What did you mean by like gain?
I was thinking like a gain medium, like a some sort of chemical gas species, like maybe like rubidium or something.
I
But
see.
in this case, it's like vacuum, right? So
I see. Okay, I see. So sort of like you have your, I don't know, let's say you have your two level system, and then you sort of have this medium where it's like these rubidium atoms are like keeping like the radiation like from keeping the radiation manipulating the relate manipulating the interaction between your radiation or light whatever specific radiation you're using and your two level atom. Is that sort of what you're saying there?
from what I understand, it would be inside the cavity, and then you would keep getting a spontaneous emission from whatever gas. But um, yeah, I think that maybe the main difference here is that we're not working in a system with a specific gain medium. So
Yeah, we're not specifically, well, we are in the sense of like I'm using like a circuit. So right, I'm using this transmission line here. Right. So this would sort of be my medium where it's like I'm sending in microwave photons that travel through this transmission line and then interact with my, let's say my transmon is here, they interact with my transmon and then I get and then they travel out. So that's sort of my medium there. I guess what you're saying is sort of your medium would sort of be like rubidium
yeah,
atoms.
for an example, yeah. But
I see.
yeah, thank you for that. Yeah, definitely. Everyone put questions in the chat. I'll ask one more and then let Carlton go ahead and start collecting these. But how does it feel to work on something that is very tied to the most recent Nobel Prize?
It's really exciting. I've been really excited to give this talk ever since I was invited to do so, and so it just makes it even more of a pleasure to talk about like why this stuff is like really cool. I mean, it's super cool that we're able to take a quantum phenomena that is macroscopic and then like manipulate that into like electrical devices. And it makes you think like, oh, what other ways are we able to then use macroscopic quantum phenomena in order to make like other kinds of like electrical devices and stuff like that. And so it's really exciting times. Really exciting times. Really feel really pumped to be working in this field for sure.
Excellent, excellent. And so, Carlton, maybe you can come on and if there's any questions, we can start cracking on those.
Uh, yes. Want to thank Alexandria again for giving a great talk. Want to thank the audience who've already submitted some really interesting questions. So we're gonna get started. Julia Niwamoto has, I guess, two clarifying questions. The first is, can you come back on what the resonant frequency of the qubit depends on?
Yes.
And then the second question is why Rabi oscillations might be out of phase.
Okay. So here we have the Jaynes-Cummings Hamiltonian and the dispersive approximation. And so here again, we have the following Hamiltonian. So here we have omega c minus kappa sigma z, the Pauli matrix. Here the number of photons minus 1/2 omega cubed omega z. Okay, so this, in order to actually read the state of the qubit, we need to use our resonator, and we can't directly measure the qubit. If we directly measure the qubit, it opens it up to the environment, and then it ends up causing the qubit to decay, and then we don't get a useful quantum system, right? And so, like, a nice way to sort of get around that is to sort of connect it to this resonator that allows us to like keep the excitation from sort of decaying out of the qubit, right? And so in order to do that, we have this dispersive shift chi. This dispersive shift chi is the difference between the ground state and the excited state. So you can sort of think of two Gaussian, two Gaussians where it's like one Gaussian corresponds to the ground state, one Gaussian corresponds to the excited state, and the difference between that is chi, right? And so if the qubit is in the ground state, then the chi shift will correspond to our photon being in the resonator. If the qubit is in the excited state, that'll correspond to our resonator being not having a photon and our qubit having the photon. And so we see this chi shift as like we send in the photon, and then this photon actually shifts by chi, and then we read that out from in our measurements. And so like we're sort of setting a phase dependent shift, right? So this would be chi, and that's sort of how we're able to measure the state of the qubit by measuring this state dependent shift, which corresponds to a value of chi. Yeah. Does that make sense?
Carlton, you're muted.
Sorry, I guess the second question for why the Rabi oscillation might be out of phase.
Oh, which one? Sorry. Are you referring to this out of phase? Was it this out of phase or? So okay, I see what she means. Okay, got it. Okay, so what this means exactly is like if we're looking at the vacuum Rabi oscillations between qubit A and qubit B, so that corresponds to either qubit A is in the excited state or qubit B is in the excited state. So in this case here, we know that if the population of P10 in this case for QA is 1, then we're looking at the state 10, which is sort of how my engine cycle started. So like here we know that qubit A is in the ground state and qubit B is in the excited state, and that's sort of why the phases are flipped. So yeah.
Awesome. So the next question comes from Bill Phillips. And the question is, well, I guess first they want to thank you for the very nice talk.
Thank you.
And they wanted to, remind us that the Nobel Committee in awarding the prize really emphasized the macroscopic nature of these quantum systems. And I guess one big part of your talk is that you point out that the system is still microscopic, in that it has excitations corresponding to one or a few flux quanta, even though billions of electrons may be involved. And they were hoping you could comment on the apparent contradiction or tension between the macroscopic and microscopic nature of the system.
Yeah, I can comment on that. So again, going back to this idea of like macroscopic systems, like macroscopic quantum systems, going back to specifically superconductivity, we have a lot of electrons, right? And the requirement of superconductivity is that as we cool down our metal filled of all these electrons at a certain critical temperature, these electrons sort of form bound states called Cooper states. So like we have these Cooper states or these Cooper pairs, where in these Cooper pairs we have 2 electrons, right? And so the nice thing about it is that usually when it comes to electrons are fermions, right? And so that's why electrons repel. Like electrons either can be in the state 0 or 1. But now that they're Cooper pairs, now by their wave equation, they act like bosons, right? So they add up, and they're able to collectively add together. So now instead of 0 or 1, we're able to do 0, 1, 2, 3, 4, 5, all the way to as many electrons in that state, like infinity, right? And so the nice thing about it is with these Cooper pairs, as we cool down our system, right, we're reducing the number of states that our Cooper pairs could go into, right? Ideally, we want to cool down our system. We want to cool down our metal such that really the only state that is available is the ground state, right? And so like we have all of these Cooper pairs, all these bosons that are in this single state, right? And so collectively they're acting as if they're one particle, but it's made of like billions upon billions of Cooper pairs that act together as like collectively one quantum particle, which is really, really cool. And that's why people are really, really interested in studying ground states and stuff like that, because you really see quantum effects at the ground state level. And so I don't necessarily want to say it's a contradiction. Like at first it's a contradiction because when you think of quantum mechanics, oh, well, why would you think like billions upon billions of atoms could collectively act in a quantum nature? But then like you sort of being able to use these sort of tricks and stuff like that, you're able to actually pull out the quantum nature of certain systems even at the macroscopic level, which is really, really cool in my opinion. So, yeah.
Really great answer. I guess trying to think if it makes sense to combine these questions. But the next question comes from John Chandler. He wants to know how you got into this field and what you studied as an undergrad, given that they're like a sophomore and they're studying electrical/computer engineering, and they'd like to know like any opportunities to work in CQED.
Yeah. What's funny is that going back to applications, I was doing work in quantum thermodynamics as an undergrad. So I did theory work in quantum thermodynamics. And what's lovely is that in order to actually do experiments in quantum thermodynamics, you sort of have to turn over to the CQED guys, right? Because they have like a physical artificial atom that you can then apply like all these things of like work, heat, and like study these kinds of things. And so what ended up happening was that after my undergrad, I was sort of looking around for like different places that I could apply to that were adjacent to what I found really interesting in quantum thermodynamics. And I found my advisor, Kater Murch's lab, because he also did a lot of work in experimentally implementing a lot of these quantum thermodynamic systems. And so that was really exciting because I was able to sort of like pivot from like theory to experiment and sort of grow my my toolkit. And it's been a really fun blast, and like I've learned so much in CQED. I would say CQED is a pretty like growing field. A lot of people are really excited, and I think I would recommend if you're going to like that March meeting, like for sure, like go over to those sessions. If you're, I guess as an undergrad, I'm sure there's plenty of opportunities as an undergrad to sort of go to conferences. I'm not sure whether at the undergrad level, I guess you would necessarily you would have to specifically be connected to a lab to go to conferences like this. But really, a lot of the stuff is also accessible online. So there's like so many talks. Like if you again pointing to the Nobel Prize winners, like Michel Devoret, if you look at his talks, he gives really nice talks about specifically like the quantum nature of quantizing a circuit. He has a specific method for it. If you look at his talks, like there's other people in the field as well, adjacent as well, like Schuster, like Jean Martins, like so many people. And they have like, you don't have to read their papers, like you just have to like look at their talks. I think that's the first starting point, and just like understand like what is going on. And then like opportunities, like reaching out, like I'm a big fan of cold emailing people just to see if they're gonna give me a chance. And yeah, it's a really exciting people, and people are really excited to bring more people into the field. And so like don't be surprised if someone's like, oh, for sure, come and join us. So yeah, I would just put my foot out there and see what happens.
Awesome. Thoughtful response. Uh, Timothy Roach has a question.
Mhm.
They're wondering if you could say a little bit about the loss factor kappa, and that is numerically or in terms of time, how long do the photons last in the cavity? And are there ways you can improve on that, or is there a fundamental limit you're reaching?
Yes. So kappa here is sort of the rate at which photons sort of decay out of our resonator. So I mean, I in an ideal world, you would want your system to be closed and it doesn't touch the environment at all, and like you're gonna get like really long really long like lifetimes, right? But it's like we need to be able to like measure our system, and so it's going to be interacting with the environment, and so it's like, as I said before, kappa sort of can correspond to the sort of transparency of these mirrors, and like the ability of the mirror, the transparency of the mirrors, and sort of how the photons sort of leak out of these mirrors. And so we want some transparency in order for us to like actually get information about our qubit system. And so the lifetimes now, I mean, it depends. Of course, it depends on like your well, this is a specific chip. It depends on whatever chips you're designing. Like, I mean, like state of the art qubits, they're looking at like, what's it called? Usually like we correspond to the decay rates in terms of like T1, T2, where T1 is sort of the decay rate of our qubit from the excited to ground state. State of the art, like 100 microseconds, like 100, 200, 500 microseconds, like somewhere like pretty high, like in the range of like hundreds of microseconds. I can't really think of the top of my head where state of the art is, but it's pretty good right now. But of course we want it to get better, because I mean there's application in this in regards to like quantum computing. We don't want our qubits to decay in order to do quantum computing, as well as quantum metrology, sensing, and things like that. So I mean the goal of people in the field, in some parts of the field, is to increase or decrease these rates of decay and make these qubits less noisy and less inhibited to decay, and like increase these T1 times. So yeah.
Awesome. And I guess the next question is also from John, and they want to know how Josephson junctions play into circuit components like JJFETs.
JJFETs. I wouldn't know what JJFETs are. Yeah, I wouldn't know what that is.
We could maybe move on to the next question. Then John also wants to know that you mentioned that decoherence is similar to entropy. Is there, a way that you can manage or reduce that?
Well, I guess what I meant by that is like more so like when you think of entropy, you sort of think about like you have your state, and sort of you think about like how your state is when it interacts with your environment, like how your entropy is always going to sort of increase, right, in thermodynamics. And so like you can sort of map the idea of like decoherence to entropy in the sense of like our quantum system is going to be open, connected to an open environment, and so like the entropy of that system is always going to sort of increase. And I directly connect it to decoherence because it's like usually in the math, that's a nice direct correspondence. But it's sort of how like quantum thermodynamicists think of entropy in that sense. So and then like not Shannon entropy. The von Neumann entropy is what I mean. So yeah. Yeah.
Awesome. I think that's the final question.
Awesome.
I want to thank you for the wonderful talk.
Thank you.
Also, for fielding the questions really well. And I'm going to hand it over to Alan to close.
Yes. So thanks again, Alexandria, and thank you to our audience. And please tune in next time for another rendition of the KITP NSBP Innovate seminar. But for now, thank you and have a good day.
Thank you.